All right, guys. I hope everyone has had a good morning so far. Um, I did finish grading this class's quiz sometime yesterday evening, but I haven't had a chance to actually put it in Infinite Canvas, if you can see how it was graded in OneNote. Honestly, I probably should have taken like 2 problems off of that. It was probably like 2 problems too long, and that might be a little bit of my bad. But then also you just want to make sure that you can find derivatives quickly and efficiently. Remember, your test grade can pull that up, and then also I am adding, from now on, any quiz corrections you do automatically adds 5 points, even over a 100. So that being said, today we are going to be looking at the next kind of application we have for the derivative. Those of you in physics might feel like this topic is very familiar to you. Those of you not in physics, it's okay. Like, I'm going to teach it to everyone like we all are at the same level right now. But we're going to be talking about a topic that's called rectilinear motion, basically talking about position, velocity, and acceleration. We won't be doing like the true like physics aspect of this. Like, we're not going to be looking at like kinematic equations or things like that. We'll define all these in terms of just like mathematical functions. But basically, this is an application of intervals of increasing and decreasing in concavity, just with some new vocabulary on it. These notes are some notes that you definitely will want to refer to really throughout the year, because we'll talk about position, velocity, acceleration. I'll often just abbreviate it PVA, like we will talk about it a lot in different contexts. So I just want to spend most of today kind of like defining it for you, and then your homework tonight is going to be you like applying these vocabulary words. And the first word I want to define is what we say by distance. Some other words that we will use for distance will be like location, position, displacement. The AP exam uses all of those words interchangeably. And I like defining this as essentially where you are relative to some fixed point. If I can spell point. And so these things like distance or like position, velocity, acceleration, they are going to connect to things like the first derivative and the second derivative. If you look to the side of the notes, you can kind of see I have it going down alongside of it. So next to the distance one, I have position and then velocity and acceleration. And that's because these can be related to the function. So like the position function is going to be associated with like the original function, so say f of x. Other common notations we're going to be seeing for position, often since we're dealing with time, we'll see like y of t, sometimes we'll see like x of t if we're measuring it horizontally. S of t is sometimes used. It's not my favorite because s often looks like a 5. But those are all the different things that we see with position. So then we have, after position, we know that we have velocity. And I like to define velocity as how fast you are moving but not only how fast you are moving, but with direction. So in math, not only can we say you're moving at like 5 meters per second, but we can know like which direction you are moving. In this class, we'll only deal with like 2-dimensional stuff. So the options for moving are going to be like forwards or backwards or up and down. So we're going to say that a positive velocity is going to mean that you are moving forwards, upwards, or it can be moving like towards the right. Like any type of like positive associated movement is going to be a positive velocity. If you have a negative velocity, that's going to be the same thing as moving backwards, downward, or to the left. So all those are kind of associated with like the negative. It just depends on the context of the problem. A zero velocity, yes, that means you're not moving. I prefer calling it means like not moving. That's definitely what it is. Key phrase though we often see for a zero velocity is this phrase at rest. And when we say something has a zero velocity, that doesn't mean like it's just like has completely stopped. That could mean that it has like even for like a small moment. Oftentimes when something is changing directions, it will have a zero velocity. So like if you think about it, if you're walking in a straight line forwards, if you're going to move backwards, there's like this brief moment where you kind of like pause and change direction. So like a zero velocity will define as being at rest, but it's often where things are going to be changing directions. So if the position equation is associated with like the original function, the velocity is going to be associated with the derivative. So like it's going to be associated with like the derivative of position, which we will often just write as v of t. But there are two types of velocities we want to make sure we define. We have the average velocity, and then we also have the instantaneous velocity. Whenever you see something like average velocity in this class, that's going to be referring to like average anything. In most cases is going to refer to us as like the old school slope formula you first learned in Algebra 1. So the average velocity is the change in position over the change in time. So I'm going to call that the change in position over the change in time, which is basically the old school slope formula. So it would have like the position at Q minus the position at P all over the change in time, Q minus P. Some things to associate this with in this class is, make that a little bit bigger. There we go. Is that when we're looking at this, the slope of what, if we're doing the old school slope, we are associating this with the slope of a secant line. Specifically, it's the slope of, if you look at the formula, we're doing the change in y, which we're associating with position. So it's the slope of the secant line on our position against time graph. Where the calculus comes into play, so like you can definitely expect to see questions asking for like the average velocity. But where the calculus comes into play is when you see something like the instantaneous velocity. The instantaneous velocity is the velocity at the certain point. So I'm going to think of the instantaneous velocity as dy dt, which we could also just simply write as y prime. It is literally the derivative at the point. So instead of talking about the change between 2 points, it is the derivative at a single point. So the instantaneous velocity is going to be associated not with a secant, but with a tangent line, but still on that position time graph. So we have position, we have velocity, and then we also have the acceleration. If you're looking out to the side, so it says take the derivative, and that's going to give you acceleration. So the acceleration is associated with the second derivative. So a lot of the stuff that we talked about with the second derivative is going to apply to acceleration. So if you're thinking about it, the acceleration is like the derivative of velocity or the second derivative of position. How we're going to define acceleration for this class is it is the rate of change of velocity let me add the calculator with respect to time. And similar to velocity, that could be positive, negative, or zero. The acceleration can also be positive, negative, or zero. Again, this is kind of like the second derivative. We know the second derivative can be positive, negative, and zero. If we have a positive acceleration, that's going to mean that the velocity is increasing, which again, that should make sense to you if you convert this to like function notation. If the second derivative is positive, it means the first derivative is increasing. So we have those connections there. If we have a negative acceleration, that means the first derivative is decreasing. The first derivative is velocity. And then if I have a zero acceleration, like it does mean like velocity is not increasing or decreasing, I'm going to define this in the calculus context, and we're going to describe it means that the graph of velocity has a horizontal tangent line. And again, we're basically taking that chart we did with like f prime and f double prime, but now we're just calling the second derivative acceleration and the first derivative we're calling velocity. Similar to velocity, we have an average acceleration and we also have the instantaneous acceleration. The average acceleration we know is going to be associated with the secant line. It is an old school slope. The instantaneous velocity is associated with a tangent line. Which graph are you looking at to identify the acceleration? It is the secant on the velocity graph, velocity time graph to be exact. Because when you think about the slope, acceleration is the change in velocity over the change in time. So our average velocity, we can write the formula as v of q minus v of t, no, v of p, all over q minus p. Whereas if you're looking at the instantaneous acceleration, it is a tangent. It is the tangent on the velocity time graph. And we can define acceleration in different ways. So it is the change in velocity over the change in time. I'm going to use the derivative notation for instantaneous. So different ways to write the acceleration. It is the derivative of velocity, which is also the second derivative of position. And so there's different ways that we'll look at these problems. Sometimes we'll look at it graphically, where it says like, here's the graph of velocity, and we'll have to make some interpretations off of the velocity graph. Sometimes they'll give you the position graph, and you have to make figure out some things and answers for that, or sometimes they give you the actual function and you have to figure out when it's positive or negative. So sign charts can come up again for these problems. The last thing I did want to define kind of pulls together two of them together. So we are going to define speed and velocity differently in this class. Velocity is how fast with direction. Speed, we're going to define mathematically as the magnitude of velocity, or to say it a little bit differently, speed is essentially the absolute value of velocity. So speed will always be positive. That's what we say when we say the magnitude. When we talk about speed increasing or decreasing, so this is different from velocity increasing or decreasing. When you're talking about speed increasing or decreasing, it's going to be how the velocity and the acceleration are kind of working together. An object is going to be speeding up in two cases. It's going to be speeding up when velocity is positive and increasing. It can also be speeding up when velocity is negative and decreasing. That last one seems a little bit weird to some people because they're like, how is negative and decreasing speeding up? But you have to remember that when I say a negative velocity, that just means you're moving like backwards or downwards. So if it's a decreasing and negative, you're just moving faster and faster in like the backwards direction. The way that we can justify this, so like the increasing and decreasing is really the acceleration. So like one way to prove that something is the speed has increasing is the velocity and the acceleration have the same sign. So either the velocity and the acceleration are both positive, or the velocity and the acceleration are both negative. And then likewise, we can assume when is speed decreasing. Speed is decreasing when velocity is positive but decreasing, or when the velocity is but increasing, or you can just summarize those together as a single statement, and that's going to be when velocity and acceleration have opposite signs. And I think that kind of makes sense as well if you think about, so like if you're moving left, but your acceleration is negative and dragging you down, like you're going to eventually be, your speed itself is slowing down. Like if someone was pushing against you while you're trying to walk in the opposite direction. So I can't do like every single problem that deals with PVA in notes. Like you can look at it graphically, you can look at it as an equation. I do think most students have trouble with it graphically. Again, I think thinking about yourself, like you're much more comfortable like finding a derivative and making a sign chart than you might be when it comes to like reading a graph. So on the back of these notes, the next page, I have some examples of just like talking about, let's just make sure we can kind of make sense of what these problems like look like in terms of the graphs, and then I have one example underneath. I don't have an algebraic one, but your homework does have some algebraic ones for you to practice. So this top part of the notes on the next page, I basically give us two descriptions. So I have like two different characteristics in the descriptions. And I just want us to kind of think like, what does that mean in terms of the position, velocity, and the acceleration, just so we can kind of make sure we see those connections. And then just talk about like what the graph of each will look like. Those of you who have taken physics, like this might seem very familiar to you, but I'm going to teach it like we're all, again, on the same page. Again, I think the easiest way to think about this is when I say position, you're thinking about F. When I say velocity, you're thinking about F prime. And when I say acceleration, you're thinking about F double prime. That tends to be the easiest way to think about it. So let's break this down and kind of see what each means. So if I say moving forward, movement is associated with velocity. So if I say you are moving forward, that statement tells you that your velocity is positive. If I say you have a constant velocity, well, if we have a constant velocity, well, clearly the velocity, I'm just going to go ahead and put kind of like constant here. But we want to see what that means in regards to everything else. So if I say that velocity is positive, that's the same thing as saying your first derivative is positive. Well, if your first derivative is positive, what is your function going to be doing? Increasing, because that would also mean that your position would also be increasing. So we can kind of make that conclusion. If I say your velocity is constant, so that's basically the same thing as saying your derivative is constant. So if your slope is constant, that means your function is going to be basically linear. And we can also think about like the derivative. So if I have a constant, so v is constant, what's the derivative of a constant? 0. So I know that the derivative of v is acceleration, so I would know that the acceleration would be 0. So kind of putting this into graphs, so like we could have a position that is increasing and linear. That's what the position will look like. Your velocity is positive and constant, and then your acceleration is 0. So that's how I can kind of take those two descriptions and make sense of it both in kind of like the chart and then in terms of just like the graph. I'm going to do the second one, then let's try 3 and 4 on your own before I just jump into it. So again, looking at this first statement, moving backwards. Movement is associated with velocity. So if you're moving backwards, that means your velocity is negative. And then it says we have a decreasing velocity. Well, if you look at the first page in your notes, a decreasing velocity, and I'm actually going to split back to it so we can see it. Decreasing velocity is associated with a negative acceleration. So going back to this chart, decreasing velocity means we have a negative acceleration. So from there, I can go ahead and make some conclusions, again, thinking about this as like a derivative. Velocity is your first derivative. It's negative, so I know that my position equation is going to be decreasing. My acceleration is with my second derivative. Well, we already said that the velocity is decreasing, so that makes sense. Think about this in terms of your function. If your second derivative is negative, then your original function is going to be concave down. So we know that the position equation would be concave down. So like drawing some basic shapes, position is decreasing and concave down. velocity is negative and decreasing, and then acceleration is just negative. Like, you may not interpret it as the acceleration being horizontal. I just know that it needs to be negative. Go ahead and see if you can try 3 and 4 on your own. And then we'll kind of go over them. Again, it's helpful if you just in your head associate acceleration with the second derivative, velocity goes with the first derivative, and then position is just a fancy way of saying the original function. So take a few moments to try 3 and 4. We'll pull all this together with a bug walking across the y-axis. Exciting stuff. And so number 3, so again, velocity deals with movement. So if moving down, that's going to be associated with negative. Decreasing speed, you want to be careful with. So when I say decreasing speed, that's how the velocity and acceleration are working together. Decreasing speeds mean that the velocity and the acceleration have opposite signs. So that's where I'm kind of giving that from. So then from there, I can go ahead and fill in the rest of it. If my velocity is negative, my original function is decreasing. Acceleration is positive, so I know that means that the function is concave up and the first derivative would be increasing. So I have a decreasing and concave up function this time. My velocity is negative and increasing, and then my acceleration is positive. So you have something looking like that. And then for the fourth one, moving to the right, that's associated with a positive movement, and then a positive acceleration. So we have concave up and increasing again, but positive means my function would be increasing. So I have increasing concave up, increasing and positive, and then positive. So where this kind of comes into play is sometimes you'll say like, hey, this is the equation for position, find the velocity. So you would take the derivative and then do some stuff with it. Sometimes you'll look at it graphically, and that's the example I decided to use today. And so this is an example of the velocity. So we are given the velocity graph. And so we have a bug is crawling along the y-axis. So it's moving basically y-axis was moving up or down. And then this is its velocity over time. And we want to answer these questions based on the velocity. So we're going to think of this graph. This is like looking at the first derivative. And we might be answering questions about the original function, or we might be answering questions about the second derivative. Number 5, it says, what is the bug's average acceleration? So big clue here, when you see average acceleration, that's asking you to just find a regular old school slope. This was actually a question that it was on a pre-response question on the AP exam. They asked you to show your work. So it's just old school slope, but you need to understand that context. So the average acceleration, I'm just going to abbreviate it as acceleration average. We know that's the change in velocity over the change in time. Well, this is the change from 6 to 0. And so I want to find the velocity at 6 and the velocity at 0. And I can just read those numbers from my graph. The velocity at 6 is 1, the velocity at 0 is 3, and that's 6 minus 0. They don't give me any units, so I can just leave that as my answer. If you're not happy with that as an answer, -2/6 or -1, I can't think third. But again, you can leave your answers ugly. Second question, again, you always want to kind of think about what it means. It says, when, if ever, is the bug at rest, and then justify your answer. Again, whenever I have to justify my answer, I like thinking about my justification first. If I'm saying at rest, what does that mean? At rest means that the velocity is equal to 0. Well, where is the velocity equal to 0 at? It's equal to 0 at 3 and 8. Again, when I say at rest in a math class, it doesn't mean like the bug is taking a nap and just like sitting by the side of the road. Like it's just briefly paused in its kind of movement across the y-axis. So it is at rest, basically when is the derivative at 0, 3 and 8. Number 7, when, if ever, does the bug change direction? Looking at this, where would you say the bug is changing direction at, if ever? Either someone at home or in here.
When time's equal to 8.
When the time's at the 8, and that is correct. So we can say, when does it change direction? It is changing at t is equal to 8 because an easy justification, so changing direction, that deals with the sign of velocity. So you can say because v of t changes sign. You could be more clear and say like changes from positive to negative, so it's going up and then down, but changing signs is the easiest way to do it. Number 8, I have when, if ever, is the bug's acceleration positive? So we want to think about a positive acceleration. If it helps, I'm going to go back to this page first so we can kind of look at it. A positive acceleration means that the velocity is increasing. So we can use that to do my justification. So if a positive acceleration means that velocity is increasing, I can look at your graph, my graph, your graph, whatever. Velocity is increasing on this interval. So on the interval from 3 to 6, because v of t is increasing. I like doing interval notation because to me it does seem to be like the easiest way to explain it. Other ways you could do, you could say something like from t is equal to 3 to t is equal to 6. That works. Or you can say on the interval 3 to 6, but again, I think you can probably agree with me that interval notation is the shortest way to write it. Number 9 is when is the bug moving upward? So the bug is moving upward. We know that direction is attached to the sign of velocity. So I'm going to go ahead and do the justification first. So it's going to be because the velocity is positive or greater than 0. Where is the velocity greater than 0? It's 0 on the interval from 0 to 3, and then from 3 to 6. There are other acceptable answers that are technically correct. I don't think most people would do them, but according to College Board, you could say not to 6. Don't be wrong. 3 to 8. Let me be correct on that. So the velocity is positive from 3 to 8. Some other ways you can write your answer that would also receive full credit is you can put a bracket on the 0 because that 3 is kind of like an endpoint and like a solid circle, so that would also work. You can also just clearly state this as the interval from 0 to 8. I personally don't like that way because we just said that the velocity is equal to 0 at 3. But since it doesn't actually change directions there, you can just summarize it and say that the velocity would be increasing from 0 to 6. The reason why you could skip over that 3 too, if you think about when we were drawing the graph, like given f prime and drawing f, if you were to sketch that graph, it would end up being more like a cubic function for that part from 0 to the 6 part. And so it is kind of increasing that whole time. Again, I like splitting up my interval, but it wouldn't be wrong if you said 0 to 8. And then this last one, we have when, if ever, is the bug speed increasing. This does tend to be the one, if I see students mess up something, it tends to be with speed, because with speed, people often interpret that as velocity, but that is going to be when two things can happen. So it's either going to be when the velocity and the acceleration are both positive, or when the velocity and acceleration are both negative. We do want to justify our answers based off of the graph given. So this one is the graph of velocity. So the speed would be increasing. Again, I'm going to do my justification first. We're going to have one case where velocity is positive and increasing. That would be when the velocity is positive and the acceleration is also positive. But the speed is also technically increasing when velocity is negative and decreasing. That's when velocity is negative and the acceleration is also negative. Let's make sure we include all the intervals that's going to fit within that. So when is velocity positive and increasing? I'm going to highlight that in green. Velocity is positive and increasing on this interval from 0 to 6. When is the velocity negative and decreasing? It's negative and decreasing from 8 to basically the edge of the graph at infinity. So this bug is speeding up on the interval from 3 to 6, and I guess this bug is living forever and walking towards infinity from 8 to infinity. But again, if students mess up something, it tends to be with speed, because you have to consider two things for speed. You have to consider both the velocity and the acceleration. Any questions on 5, 6, 7, 8, 9, or 10? All right, for the sake of time, I'm not going to do number 11 with you. Number 11 is just to sketch the acceleration and the position, but that's really just a review of if you think that velocity is like the derivative, going from velocity and trying to draw the acceleration is like going from y to y prime, since acceleration is the derivative of velocity. But if you're going from velocity to the position, that's going to be like where you do the derivative and then the original function. We often don't have to draw out those graphs. I do have in the homework you to review that, but for class, I'm going to save time and skip that last question. Yeah. So your homework for tonight, I guess you could do quiz corrections since I've graded yours already, but the only homework I'm assigning is homework 5. Please read the instructions. I'm only making you do the odds or the evens. I already forgot which one I did, but you're only doing half of them. You can do all of them if you want to do the extra practice. That is also what you're working on for asynchronous day. Like, I'm not going to have a meeting. I'm not requiring anything of you on Wednesday. So you can just use today and tomorrow to work on the position, velocity, and acceleration homework. The first half of that homework is going to be graphically, just like the notes we did. The second half of that homework is you're given like actual equations to find the position, velocity, and acceleration with. When we return after the asynchronous Wednesday on Thursday, we will be doing something called implicit differentiation. Those notes will probably take both Thursday and Friday. If you have a lot of time on Wednesday, like I know all of y'all have to be more busy than to have extra time. But if you have extra time and want to get ahead, there is another set of AP problems for this unit, and that's under homework 7. Some of the problems in homework 7 are implicit differentiation, which you can't do yet. But one of the problems does deal with velocity, acceleration, and position. So if you are looking to get ahead, you're more than welcome to start homework 7 and do the ones dealing with PVA. But really all you want to make sure you're keeping up with is just homework number 5. So I'm going to go ahead and end the live session of class. So if you're at home, feel free to go ahead and log out and ask questions, or ask questions if you have them.